execution using the backends. So the backend, as this slide shows here, is an acceleration library that implements the neural network operations. It can be an interface to a hardware device or different libraries that run on the CPU. So in Blue Box case, we have the KN backend. So this is for the Cowray MPPA accelerator. And having this included here within the EIQ Automotive framework, this hides the complexity of running a model on the Cowray MPPA, but you still have all of the flexibility to interact with other Cowray services. We also have an ONX runtime backend. ONX is an open source inference engine which can be used to execute any compliant ONX model on a wide range of CPU options. This backend is mostly used for prototyping and model validation. And we have the IR backend, which is still in development, and it's a SPICE compliant implementation of these cooperations. The other parts of the EIQ Auto runtime take care of the data movements, the translation and connection between the backends. It automatically transforms the data layout and format when it's needed and optimizes memory transfers between them. So it handles execution scheduling on the backends. The offline tools supports TensorFlow and ONX models, and also prepares the neural networks for heterogeneous execution by partitioning the model into subgraphs and assigning them to the available backends. In this case, we're referring to the Blue Box 3 backends. So it optimizes the workloads for different hardware targets. So again, just to reiterate, in the Blue Box case, we can deploy on the Cowray, the MPPA accelerator. So we have integrated the compilation of the MPPA graph. So a key aspect of EIQ Auto is the partitioning of the model into these subgraphs to enable the heterogeneous execution of the different backends. So starting with a graph that contains multiple operations, the model is split into subgraphs by considering different factors, such as what backends are available, and what type of operations are supported by the different backends, and the performance of the execution of the different backends themselves. So now let's look at an actual example using a commonly deployed neural network for object detection, the YOLO V3, and the steps that would be worked through to deploy it on the Blue Box platform. So YOLO V3 is an encoder-decoder architecture. The encoder does the heavy lifting in that it works to detect different structures in the image and at different scales. It contains classical operations as part of convolutional neural networks, which themselves require high computation. On the decoding side, the results produced by the encoder are filtered and bounding boxes are applied. The amount of data at this stage that needs to be handled is considerably lower than the encoding stage. So that means that we want to run the encoder, the detector, on the MPPA and run the decoder graph using the ONX runtime backend on the LX2 to produce the decoded boxes. So this is all done using the offline tools. So starting with a TensorFlow model, in this example again, the YOLO V3, and a set of annotations. These are layers that specify where the splits should be made and the targeted backends. So the KNN for the first part and the ONX runtime for the latter. The graph splitter then does the required splitting. So the encoder is compiled using the KNN compiler, and the decoder is converted from TensorFlow format to the ONX format. And the output from those two together, with some graph meta data, are exported to form the EIQ Auto model. This model is then deployed on the target hardware using the EIQ Auto runtime. So at runtime on Bluebox, in this example, I want to show how all of these are put together, not just at the component level, for example, the LX2, but at the system level, which is more representative of the setup at our automotive customers. How do you achieve high and optimal utilisation of the available resources within the system? So a quick recap first of the system in this example. We have a CAN card, we have the MPPA, the LX2, which is the master within the system, and the main applications run there. The LX2 communicates with the CAN card and the MPPA. So the LX2 first configures the CAN card using the CAN card client, and then the peer-to-peer communication between the CAN card and the MPPA directs the streaming of the image directly into the MPPA. So the MPPA architecture then performs the pre-processing of the network, which runs a subset of clusters, and the other clusters on the MPPA are utilised by the EIQ Automotive toolkit. Pre-processing the image uses a custom OpenCL kernel. After this, the EIQ Automotive execution is triggered, so the detector is then run on the MPPA. After the results are transferred to the LX2, the LX2 uses the ONX backend and post-processes the results and plots the final image. So all of this happens without extra buffering or redundant copying. EIQ Auto is a key enablement toolkit for customers and needs to be part of the complete toolchain that customers can easily and quickly utilise. To show the approach that we've taken on how customers can use EIQ Auto for Bluebox 3, I'll first summarise the complete Bluebox 3 SDK that EIQ Auto is part of. However, the very first automotive processor that was supported by EIQ Auto, the S32V2 Vision and Fusion processor, EIQ Auto was standalone. It was a standalone package. For Bluebox 3, we integrated it into the SDK. Our SDK is based around maximising user space, application and library development for the LX2, the S32G and accelerators such as the Cowray MPPA. We provide a Linux BSP for all of the devices as a base, from which we build further enablement on top of. In particular, we include the middlewares for inter-device communication, such as DDES and ROS. And we also include machine learning, like EIQ Auto, or Cowray's CAF to fully enable an efficient and structured AI/ML application, such as perception for automated vehicles. So after install, you can immediately start writing your own code without having to install separate compilers and so on. Deep learning has proven to be an approach that delivers higher accuracy, which is especially important in the ADAS AD domain. The layer structure of neural nets makes them very well suited to tasks such as image classification. That is why EIQ Auto was first deployed on our S32 Vision processor. Since then, we have seen AI/ML moving into other areas of the vehicle, such as user experience, powertrain management, security, amongst others. Hence why we now have EIQ Auto also supporting the Bluebox 3 platform and our S32G networking processor, with future S32 automotive processors support also planned. Ali, I'll hand back to you now for the overall closing statements.
Thanks a lot for that, Mark, for the intro and additional information on EIQ Auto. As we've tried to present and give you more information around the enablement at NXP around machine learning, it is a fundamental component of NXP's offering in the machine learning domain. So both EIQ and EIQ Auto are software development environments and tools that NXP offers to support your application